Welcome everybody to the 2023 Watershed Congress. My name is Faith Zerby. I'm Director of Monitoring with the Delaware Riverkeeper Network, and I'm the moderator for this session, a global and local look at how plastics enter streams and how to design experiments to monitor macroplastics. We've got Ann Faulds and Carol Armstrong, Friends of the Heinz Refuge, Kaitie Evers from School Action Network, Partnership for the Delaware Estuary, and Tim is joining us virtually in a presentation from the Wageningen University, all the way from the Netherlands. So Anne, I'll let you take it off from here.
Thank you very much. And once again, welcome to the last session of this year's Watershed Congress. I also would like to give a heads up that there will be two short pauses when where Kaitie will lead a reflection session on Tim's presentation. It'll be like 5 minutes. Now I'd like to just pass the baton to Carol, who will tell a little about the pre-recorded encore presentation for today.
We're very pleased to have Tim van Emmerik present this lecture for us. He is an international expert on the problem of macroplastics in rivers, those plastics that are visible. He is currently assistant professor in hydrologic sensing at the Wageningen University in the Netherlands. He obtained his PhD at the Delft University of Technology and then worked at the Ocean Cleanup to develop their river plastic research program. He leads the Wageningen River Plastic team. His team aims to advance the field of river plastic by one, developing measurable methods, and two, with river basin scale assessments of plastic pollution, which we're going to learn a lot about today. His team champions the use of drones, cameras, and satellite remote sensing for plastic detection in rivers, as well as citizen science. The team's work has revealed many new insights in quantities and transport processes of plastic pollution in rivers around the world, including I'll admit just all around the world. Tim is a member of several scientific advisory committees for the United Nations and for the Netherlands Ministry of Infrastructure and Water Management. So as amazing as his background is, what he's going to teach us today is useful for all of us who may want to be understanding the problem of plastics in our local freshwater streams. Thank you.
Okay, well, good morning again. My name is Tim van Emmerik. I'm an assistant professor hydrologic sensing at the Wageningen University and research in the Netherlands. And I'm one of the specialists that focuses on river plastic monitoring. And not just river plastic monitoring, but macroplastic monitoring in river systems. What we talk about macroplastics, I'll share with you in a minute. But I would just like to start this presentation with a brief intro about what we're going to talk about and with a short introduction about me and my team. What I want you to remember from today's talk is that only a very small fraction of all the mismanaged plastic waste in the environment actually makes it into the ocean. And the more we try to measure plastics in the field, the more we find that plastics actually accumulate in terrestrial and riverine environments. And only a very small portion flows into the ocean. It has quite some implications for plastic monitoring, and because it is quite difficult, there is unfortunately no silver bullet for river plastic monitoring. So in the end, if you're designing your monitoring strategy in your system of interest, you will always have to make a trade-off between your locally relevant questions and the available resources. A little bit about me and my team. At Wageningen University, we focus on 3 key aspects with regard to plastic monitoring. First, we focus on method development, so developing techniques and protocols and guidelines on how to quantify macroplastics in and around river systems, ranging from low-tech techniques to more high-tech techniques, about which I'll share some examples later. But those include very simple visual surveys by citizen scientists, the use of cameras, remote sensing, drones, and other devices. Secondly, we focus on monitoring strategy development, so that is really translating specific methods into strategies for river basins or countries or urban water systems to answer the societal and scientifically relevant questions using science and monitoring. So we do that in the Netherlands for Dutch rivers, but we also work together with partners in Southeast Asia, for example, to do that for other river systems around the world. Finally, the third aspect of our work is to use the science that we produce and that we produce with our colleagues for impact. So that is really trying to make sense of the data that we collect and use that to answer relevant questions for science and society. So for example, questions about what are the sources of plastic pollution, what are the sinks or accumulation zones, what are the quantities that you can expect in systems, what is the composition of the plastics, what kind of items can you expect, and what is the impact of all the plastic pollution in riverine or other freshwater ecosystems. And with that science, we hope to contribute to effectively optimizing prevention, mitigation, and cleanup strategies in systems around the world. And what we talk about when we talk about plastic is macroplastic. So plastics come in all different kinds and sizes and sorts. And quite roughly, we can distinguish between microplastics and macroplastics. Microplastics are all the plastics smaller than 0.5 centimeter. All the macroplastics are the plastics larger than 0.5 centimeter. I'm not sure how much yards or inches 0.5 centimeter is, but it should be about this. The good thing about macroplastics is that you can easily see them with the bare eye. And it's also actually the macroplastics that cause most known negative effects of plastics in the environment and for human livelihoods. So if you look at the types of plastics that kill and injure animals and plants, it is mainly the larger pieces that are ingested by fish or birds. It's the larger plastics that get entangled in mangrove forests and lead to death of these plants. And it's also the larger plastics that are causing damage to, for example, vessels and infrastructure. So here you can see two examples of, it's actually quite ironic because in the bottom left picture is the one time I went out to sample microplastics, and our ship and our net got completely destroyed because we got stuck because a very big piece of macroplastic got stuck in our vessel. The upper right picture shows the accumulation of macroplastic in an urban drainage system, and we demonstrated that plastics actually lead to a faster and larger water level increase when it's blocking urban drainage infrastructure. So it actually contributes to additional flood risk in areas that are already sensitive or prone to flood risk. And finally, if you're interested in microplastics, macroplastics are the main source of microplastics. So by tackling macroplastic pollution, you also tackle microplastic pollution. The whole field of plastic research and initiatives to tackle plastic pollution started with the discovery of the plastic soup some time ago. So it was founded in these so-called gyres around the ocean. Plastics tend to accumulate because of the natural currents that are bringing the plastics from coastlines and from the ocean to these accumulation zones. And one of the most, maybe well-known and well-studied plastic gyres is the so-called Great Pacific Garbage Patch located between Hawaii and California. Maybe you've heard about this, but this is the place that is, I would say, the most polluted or known most polluted piece of the open ocean around the world. To put some numbers on it, we find about 100,000 tons of plastics floating in an area 1.6 million square kilometers. So that's, I think, 2 times the size of Texas or 3 times the size of France. Now, it sounds like a lot, and it is, but maybe later we'll put it into perspective and see how this number relates to what we find in other ecosystems, such as rivers. One of the main questions that was then asked by scientists and others is, where is all this plastic coming from? Why is plastic accumulating in the ocean? Where is it originating from? And quite soon it was already discovered that most of the plastics that you find in the open ocean, that they come from land-based sources. And through all kinds of natural processes and human dynamics, plastics are either directly emitted from coastlines, or they are transported through river systems into the world's oceans. One of the key aspects here is that more and more effort has been put in better quantifying and estimating how much plastics are in the end transported from rivers into the ocean. And that led to a huge increase in research efforts and all kinds of initiatives to better measure plastic in and around river systems. And the more data has become available and the more observations have been done, the more we actually see that it doesn't seem like plastics are to a great extent flowing into the ocean. And it actually seems that most macroplastics does not flow into the ocean. Actually, the more data, more observations we have, the more we see that plastics accumulate in all kinds of compartments of the river system. So yes, plastics are leaked into the environment from industry, from consumers, from direct littering, through all kinds of processes related to wind and river flow and floods and anthropogenic influences. They are mobilized in the environment and into river systems themselves. But then most plastics seem to get stuck somewhere. Either it accumulates on riverbanks or in the floodplains. It gets entrapped in vegetation. It accumulates at infrastructure such as sluices or dams or ports and other kinds of waterways. It can get entrapped in floating vegetation, and it can accumulate in estuaries because of the tidal dynamics and the bidirectional flow. And in the end, at the global level, we think that less than 2% of the total amount of plastic that is leaked into the environment is flowing into the ocean. And that brings us to the main question of our team, and that is the question, what happens to all the other plastic? Where does it stay? Where does it end up? And for how long is it retained in those environmental compartments? So the main research questions that we work on is first, how do you actually measure plastic consistently over time and space? How do you make sure that you collect data in a consistent way so that you can compare the dynamics over time and space, that you can compare river systems, and that you can see if there's any hotspots in time and space? And secondly, if you have data available, we are interested in what are the sources and the sinks and the transport dynamics that these plastics are experiencing in the environment. And finally, how do we use data and the science to optimize prevention and reduction strategies?
Okay, let's pause and reflect on what we just heard there. I'm going to go back to Mentimeter and flip to our second slide here. What are your project planning challenges? So you can refresh your page if you're on your phone connecting to Mentimeter. Go ahead and hit next slide. Or if you're signing on for the first time, you can go to menti.com and enter the code shown here. There we go. Now we can see your answers. There we go. Storm drain awareness. It's a big one. We're just going to take a moment to reflect.
I just want to mention that if you'd like to post something about work you're planning, that's fine too.
Thank you. You know, plastic bag bans are starting to come out about more frequently, so we look forward to that. But as we continue on to our presentation here, I'd like you to reflect on what Tim's saying in context of your own projects that are going on. So we can go ahead and resume the video. Tim is going to discuss the different research methods he uses in this next segment.
Now, I've been measuring a whole lot of rivers in my life, and unfortunately, you find plastics everywhere. It doesn't matter if you go to the field in the Netherlands or Norway or Switzerland or Ghana or the US or Vietnam, you find plastics everywhere. And you find plastics in all kinds of compartments of a river system. So obviously, you can find them floating at the surface, but you also find them below the surface in the water column. You find them on the riverbed, in the sediment, deposited on the riverbanks, on the floodplains, and in the riparian vegetation. And our key objective is to develop measurement methods to be able to consistently quantify the plastic abundance in all these different river compartments. And in the remainder of the talk, I would like to focus on a couple of strategies that we have developed to quantify plastics. And after that, I'll give some examples of applications in the field, and I'll give some guidelines on how you can use that knowledge and that experience to design your own monitoring strategy for a system of interest. So very short, I think, in summary, all the available monitoring methods can be distinguished or separated in more or less 5 to 6 measurement technique categories, ranging from collection on the left to counting methods, to the use of drones, cameras, and finally the use of remote sensing. I actually added a 6th method, but I'll come back to that later. So collection-based methods are, I would say, the most straightforward ways of monitoring plastics in river systems. And those are maybe also the methods that scientists and citizen scientists and practitioners are also tempted to use instinctively at first. And well, what does it mean? It means that you either actively or passively collect a sample in the environment, which you can use for detailed analysis. Well, with active and passive sampling, I mean the way that your sample is being collected. So you can actively go to a river system with a net or with some other device and try to collect waste or plastics from a river system. But you can also do that more passively and, for example, go to places where plastics are already accumulating, such as you can see here in the bottom right, in a litter trap that is purposefully installed to accumulate plastics in a river system. But the same holds, for example, if you go to riverbanks or try to collect plastics from places where they already naturally accumulate. And based on this and based on your research question, you can go to as much detail as you'd like. So you can categorize the samples into either very specific or very broad categories. You can measure the size and the mass, even the specific polymer type, and you can try to estimate all kinds of indicators related to the origin, such as name tags or labels, languages, the state of biofouling, etc. The second type of techniques relate to the so-called visual counting methods. And visual counting methods is, for me, my method of preference, my method of choice, because it is very simple. What does it mean? Well, it means that you literally just count plastics at a place for a certain amount of time. And you can do that either on bridges or on riverbanks. And I'll briefly explain how that works. So what we normally do if we are asked to estimate the amount of floating plastics in a river is that we use the visual counting method to assess floating plastic from bridges. So what we do is we go to bridges, we divide a bridge into a number of segments, and for each segment, we can do measurements. And a measurement means that we stand on the bridge, we look at the surface, and we count all the floating items for a specific amount of time, let's say 10 or 15 minutes. And that allows us to very rapidly estimate the amount of floating plastic transport in terms of items per hour. At the same time, you can also do that on riverbanks. So you yourself, or you can ask volunteers to go to riverbanks and on a predefined sampling area, count all the items that can be found there. The nice thing about these methods is that they are very simple. They can be done by everyone, but they're also very consistent. So what we do is we apply these methods with school kids, with students, with citizen science all around the world. And that allows us to directly compare the data that we collect, for example, in the Netherlands to the data that we collect in Ghana or Vietnam. One of the things that you can add is you can add mass statistics of the plastics that you find in the river, because so far we've been expressing plastic transport in terms of items per hour. But if you know what the mean or median mass of an item is, you can also convert these measurements into mass transport in kilograms per hour, kilogram per year, tons per year, you name it. The other nice thing about this method is that it's a very powerful tool to arrive at a first order estimate of transport and hotspots. So what you see here in the lower left is a comparison of the seasonal plastic transport for 3 locations in a river system. Well, you directly see that there's a clear difference for specific locations in the river, and you see that there's a very clear peak in this case in February, which was related to the high water peak in that river, the River Meuse in Western Europe, that is. On the right-hand side, you can see how you can use those measurements for comparing average statistics. In this case, we're comparing, I think, 7 measurement locations, and you can directly see that there is an order of magnitude difference between these locations, and you can also see that they vary quite a bit over time. So again, that emphasizes how you can use these easy measurements to get a first order estimate of how polluted a river or a location in a river is in terms of floating plastics. Then on to the more advanced techniques. One of them is the use of drones. and specifically drones with RGB images or video footage. And these are very good. This is a very good method if you are interested in measuring floating plastics at locations where there are no safe bridges. So, for example, if you're interested in very wide river sections, or if you're interested in more complex estuaries, then using drones can be a solution because you're not depending on the available infrastructure there. There are unfortunately also many practical constraints. They relate both to the instrumentation. There's always like the limited battery life or battery duration for a drone. So normally you can only fly for about 20 to 30 minutes. But there's also a lot of legal constraints in many places. So for example, in the Netherlands or in France, we're not able to just take images with drones because privacy regulations, you name it. So in those places, we just simply cannot use drones for plastic monitoring, unfortunately. And the second challenge, or the third challenge, relates to the data processing, because all the images that you collect or all the videos that you collect, they have to be processed, they have to be annotated, they have to be converted into actual data. And you can either do them manually, or you can try to use some sort of machine learning or artificial intelligence algorithm. And I know that sounds very promising, and there's a lot of great effort being done to develop these AI algorithms for automatic detection. Unfortunately, we're not really there yet for any plug and play solutions. So you still have to really manually process a lot of images before you can get any meaningful results for specific river systems. I would like to end the part of the drones with a positive note, because what you see here in the lower graph is an example of the results that they can generate. And in this case, what you see on the x-axis is the time. On the y-axis, you see the river width, and the size of the bubble illustrates the amount of plastic that was measured at that specific time and space. And what you already see is that because of the monitoring that we did, that we could actually see this very clear variation over time. So during some moments, the bubbles are much larger, indicating much more plastic. But we also see that there's quite some variation over the cross section of the river, meaning that there could be preferential areas of plastic transport. Now, why is that relevant? Well, first of all, it may say something about the potential sources of plastics. Is there maybe a point source on the left or the right riverbank? But it also can inform stakeholders to plan any intervention measures. So if you're interested in collecting waste, should you, for example, install something on the left side or the right side of the river? And with this, we can already give some preliminary answers to that question. Then on to the cameras. That's, I think, another very promising and popular method for plastic monitoring. Well, we tested that ourselves as well using RGB cameras. We tested it for a first application in Indonesia, one of the places where we assume that there is quite some plastic pollution in the rivers. And we tested this on 5 rivers in the greater Jakarta area, the capital city of Indonesia. And what we found is that in the end, the performance is okay. So again, with performance, we mean the whole performance from the collection of the images, the training of the algorithm, and then the application of this algorithm for automatic detection. And in the end, we were able to, I think, detect about 60% of the manually detected plastic items. And that is okay, I would say. Unfortunately, we also found that the transferability is very low. So if you design or if you train an algorithm for one river, it cannot be blindly applied to a different river. So that means that this whole effort of training an algorithm and annotating images yourself for now needs to be done for each individual river that you're interested in to monitor using cameras. Also here, I'd like to end with a positive note. Again, on the bottom right picture, you see the comparison of the plastic transport measured by humans through the visual counting from bridges in dark blue, and the measured plastics using the cameras in light blue. And what you see is that in general, the temporal dynamics are quite similar. That's what I mean with the performance is okay. But we also see that especially during the peaks, there's quite some discrepancy in the amount of plastics that were detected. And I think that's actually, we can explain that by the fact that at some point, there's just too much plastic for people to count. So I'm not sure if you've ever counted plastic yourselves, but if you have to count more than 100 items per minute, I can tell you it becomes very tiring, and you'll probably start missing some pieces. The benefit here is that if you have cameras and images, is that they don't have the same struggles, and they can actually outperform, it seems, human observations during peak flow events. Then there's the even more advanced techniques, and this is also more work in progress, but it is basically shifting from these classical images and videos using RGB to exploring near field and spaceborne remote sensing using hyperspectral and multispectral cameras. In short, what that means is that we're trying to use different wavelengths in the light spectrum. So not just the colors that we can see as humans with our eyes, but also different frequencies and wavelengths in that light spectrum, including infrared or near infrared. And what we actually find is that at specific frequencies, plastics can very well be distinguished from other materials, from water, from organic material, and we are actually able to distinguish different kinds of plastics using multispectral imagery. And that is also quite promising, but because that means that we cannot only just detect plastics accurately in river system and the ocean, but we can even say something about the type of plastics that you can expect in these systems. We're currently exploiting that for field-based sensors, but we are also really pushing to use all this knowledge for the design of future Earth observation missions, because I do think it's possible in the end to develop spaceborne remote sensing missions that are able to detect and monitor plastics from space. Then finally, so far we've been mainly focusing on plastic monitoring at the surface or on riverbanks, but unfortunately there also seems to be quite some plastic below the surface, and unfortunately the deeper you go, the more difficult it is to measure plastics. So far plastics below the surface are mainly being monitored using nets that are deployed using ships or big cranes from bridges, but it's extremely cost ineffective, laborious, and just expensive. So we're also exploring alternatives to detect plastics below the surface. And one very promising method is the use of echo sounding or sonar, where through sound waves, you can detect plastics below the surface. And an example of what you can expect is what you see here in the upper middle figure, where you see 4 reflections. The ones in the middle are typical reflections of fish. They are a curvy banana-shaped figure, but you also see a plastic bottle and a plastic bag that we were able to detect below the surface, up to 3 meters deep. So I think that's really quite promising. But when we did this for longer, for a couple of days, we also found that for this specific river in Spain, where we did the measurements, almost 80% of the total plastics were found below the surface. So that stresses again how important it is to also invest in the subsurface detection and monitoring of plastics.
All right, let's take a moment to digest everything Tim just went through there. I'm going to bring up a new Mentimeter slide. Share my screen here. I'm going to hit refresh. I'll be switching this over, but Tim discusses 5 different methods of surveying here. And here we are. So if you hit refresh, you should be able to go on to this next slide. So the 5 different ones he mentions are collection, counting, drones, cameras, and remote sensing. And we were curious to see if any of you have thought about using any of these or do use any of these in your projects. We'll take a moment to reflect on those different methods. It can be tedious. This kind of work helps us learn how big the problem is and what sorts of things are coming out of the system. So, great. Thank you for responding. I know the counting can be tedious. And we are going to move on to one of Tim's next topic here. On why plastics must be in the conversation about when we talk about flood mitigation.
Well, this is a summary of the way that we've been measuring and are measuring plastic right now. But I also want to stress that with the increasing knowledge and experience that we have, is that we also find all kinds of new driving forces of plastic transport and retention. And that complicates things, but it also offers new opportunities. So just to illustrate, we've been trying to explain the variability in plastic pollution in Dutch rivers, and still we think that that hydrometeorology, so wind, river discharge, flow velocity, that all these natural driving forces are governing processes of river plastic transport. But we actually find that only 40% of the plastic variability can be explained by these factors, meaning that we just don't know enough about plastic dynamics and plastic transport in rivers to actually say something about what drives transport, or how we can better measure or model this. And that is also because there's all these new important factors that we keep on discovering. And to support that, I'd like to illustrate this one example from Vietnam, where we were trying to explain the seasonality of plastic pollution in the Saigon River using discharge and rainfall and human activities, etc. Well, we couldn't find any explaining variable there until we started looking into the presence of so-called water hyacinths. And water hyacinths is an invasive species. They have, well, occupy basically every subtropical and tropical river around the world, and they grow very rapidly. And we found that the only explaining factor of the amount of plastic pollution in this river was the abundance of these water hyacinths. And what you can already see on the picture is also the reason why that is, because these patches and these plants are not only very effective in growing themselves, but they're also very effective in entrapping all kinds of materials, including plastics. So better understanding the driving factors also informs how you should go about monitoring plastics in the river. And in this specific case, we're actually using these hyacinth patches as a proxy for plastic pollution. Why? Because plastic pollution cannot be detected from space, but these very green vegetation patches are visible from space. So by using satellites, we can see, in how many river or how many plastic or how many vegetation patches you find in a river. And we know from the field that there's a correlation between these patches and plastics. Then some other very important driving forces or explaining factors that we found in the field. One example is from the case of Ghana, where we found that plastic pollution and floods are very closely connected. Firstly, because what we showed is that that the plastic that is being mobilized, it clogs urban drainage infrastructure, leading to additional flood risk. And because of this flood risk, more plastics is mobilized. So there's this nexus between plastic and floods in systems like this. And well, I think the pictures here that they say enough about how urgent it is to better quantify and reduce plastic pollution in systems like this. But it's not only places like Ghana where floods are important. Maybe you've heard about the devastating floods in Western Europe last summer, in July, in Germany, in Belgium and the Netherlands. Because of our monitoring efforts, we were able to quantify the amount of plastics in the River Meuse during this flood and after the flood peak. And the results were really surprising because we found so much more plastic than just plastic waste. We found mattresses, Tupperware boxes, fridges, you name it, stuff that you don't typically find in river systems. And we quantified that there was 10 to 100 times more plastic floating in the River Meuse compared to normal situations. So this again also demonstrates the complex dynamics and the very important influence of floods, and also the need for data to show that that is actually the case. Just to zoom in on the data that we collected there, what you see here is in gray, the hydrograph, so the river discharge for the full year of the River Meuse. And the markers illustrate the amount of floating plastics in the Meuse during a measurement campaign. And I think this already says enough. During the flood peak, there was a huge increase in plastics. You could also see on the right-hand side that the amount of plastic pollution nicely follows the hydrograph. So there seems to be an almost linear correlation between plastic discharge or between river discharge and plastic transport. And that can be quite informative for better understanding how much plastic is transported, but also in terms of designing prevention methods and monitoring strategies. Finally, I'd like to mention some of the challenges, and those are the issues of skill and time, because it really depends on the skill and the spatial and the the temporal scale in terms of what monitoring strategies are most suitable. To illustrate that, I have 3 examples of completely different river systems. On the left, you see a typical urban river. In the middle, you see a natural river. And on the right-hand side, you see a river mouth. And I would like to ask you to think about which of these 3 rivers you think is the most polluted. Well, maybe you think it's the left picture, the urban river, but I can tell you these 3 rivers are equally polluted. The reason why that is because we were measuring in all these 3 rivers, ranging from Ghana on the left, Vietnam in the middle, and the Netherlands on the right. But unfortunately, we're sometimes a bit biased if we only see pictures of the left kind of river, and we tend to forget that also rivers in Vietnam or the Netherlands or the US can be extremely polluted. And it's really, I guess, the power or the power of these simple measurements that allow us to directly compare the amount of plastic pollution in these very different river systems. And there's also the issue of time, because we show that the more data you have for a river, the more it seems to vary. We already demonstrated that plastic pollution can vary multiple orders of magnitude during the year, which I think really emphasizes the need of baseline studies. Because if you have a baseline study, you also can better assess whether the plastic pollution that you measure now is relatively high or low. Also, as we discussed, hydrology is very important, so keep that into account when you're designing a monitoring strategy. And it's very likely that flood events have a major effect on the amount of plastics in your river system. So take that into account if you're thinking about how to quantify plastic pollution in your river system of interest. Well, for those reasons, we're also working on the harmonization of measurement methods, because it's really key that we start comparing rivers around the world and we start comparing data collected within river systems at different locations and different times of the year. So luckily, that is already possible with the data that we have. To some extent, we're able to now compare some rivers in Europe with Asia, and we already see that rivers can vary greatly around the world, 6, 7 orders of magnitude, and the same also within river systems. So we showed that that within the Netherlands, we measured plastic pollution along the River Rhine and along the River Meuse, and you have very clear peaks of increased plastic pollution for which we have no explanation yet. But what this does show is that these basing scale assessments are really important to better understand the state of plastic pollution in a river system. And this is really the basis for answering any fundamental questions that you have regarding the sources, the sinks, the retention times, and also the effects of plastics on specific river systems. I'd like to close off with a workflow that we developed specifically to help designing monitoring strategies for quantifying microplastics in river systems and other freshwater environments. And this workflow consists of 5 very simple steps. The first, and I think most crucial step, is that you should always think about what is the reason why you want to collect data. So what is the question that you want to answer? And the question could be, what is the emission of plastics from a specific river into the ocean? It can be, what is the top 10 or 20 most abundant specific item in a river system? Or, for example, are there specific hotspots of plastic pollution in a river system in time or space? Secondly, it's key that you understand how your river or freshwater system looks like and what the characteristics are of the system. Are we talking about a very wide system, such as a river mouth, or are we talking about a very narrow system, maybe in a more urban area? Are there any safe bridges available? What is the available infrastructure? Are you close to the road network or to a port or a waterway? Are you measuring close to the river mouth where there's maybe tidal dynamics, or at a more upstream location? And thirdly, always be very critical and realistic about the available resources, because we can already, I can already tell you, if you want to measure everything all the time, everywhere, it's not going to work because it will cost you a lot of money. So ask questions about how much funding is available for monitoring. How many observers do you have at your disposal? Can you invest in high-tech technology, or are you restricted to low-tech equipment maybe? So what is the budget that you can allocate for your monitoring strategy? And fourth, think about the data that you need to collect. What kind of units do you need, or in what kind of units are you going to express your results? And is the data that you're collecting consistent with your question? So if I want to say something about the emission into the ocean, and my data reports something about the relative abundance of specific items, it's not aligned. There's a mismatch. So to make sure that your data is consistent with your questions. And then finally, analysis and dissemination. Always think about very carefully about your visualization, because if your data is not reported well, documented well, or visualized well, it will not inform scientists, policymakers, or the general public. So consider the stakeholders in the analysis and dissemination of your data and your results. And then finally, again, always do the final check. Are your questions being answered? And if that's the case, you did a great job. And if that's not the case, then you have to go back to the drawing board and basically go through the workflow all over again. That's not a bad thing, because designing monitoring strategies is not a linear approach, but it's an iterative approach. So through learning, through identifying your goals and your open questions, you know how to move forward. You know, based on your river characteristics and available resources, what kind of monitoring strategy is right at this very moment. But based, of course, on the insights that they generate, you may want to refine your monitoring goals. There's maybe new funding or different resources available, and you can go through this whole design cycle again. If you're interested in this and you want to work yourself on designing a monitoring protocol for rivers or estuaries or other freshwater environments, I'd like to invite you to have a look at the UNEP monitoring guidelines for plastics in rivers and lakes, or to have a look at their recent publication on a roadmap for long-term microplastic monitoring in rivers. So again, in conclusion, what I want you to remember from this talk is that only a very small fraction of the amount of plastic waste in the environment makes it into the sea. It's still a big question where it remains, but we think that most of the plastics are accumulating within river systems. Unfortunately, there is no silver bullet for river plastic monitoring, because in the end, it always depends on the trade-off between the local questions, the river characteristics, and the available resources that you have at hand. And with that, I'd like to thank you very much. Again, my name is Tim van Emmerik, and I would be very happy to answer any questions that you have.
All right. So it's almost 2 o'clock here. And since Tim is not available to take your questions, if you have any for Tim, please put those in the Q&A along with your email address so we can get back to you. And I know, thank you, Carol, for responding to some of the questions that have been popping up about more local issues. So we would like to thank everyone for attending and sharing with the group today. And we would like to thank Tim van Emmerik for sharing his experience in this presentation. And I would like to leave you on a final reflection point. How can you take this information and implement it?
May I add something to the reflection? You know, while Tim showed how much there is to think about and also how much they've learned, which is so impressive, please remember that really all you need is the right question to start with. He does talk about resources, and you can take that all into account. But once you have the right question that you want to ask, I think you'll find that it can lead you to having more tools for your advocacy, more understanding yourself, more sources for education. I mean, it will be the beginning of giving you a less sense of helplessness and more actual information. So there's another question here. I'm just going to read it since we have a couple of seconds. Maybe you can do something locally, Will asks. If you are in college, you can start a group and hopefully get support from your community. So, I mean, that's the thing. This can be approached from your neighborhood street, from your college, from your children's school, from your church, from anywhere. And it's just, you know, figure out what the question is that you all can work towards.
Ladies, we do still have about 7 minutes. So if there's other things we want to talk about, feel free to do that.
I will mention that in the Schuylkill watershed, the Schuylkill Scrub is currently going on through May 31st. It is an initiative where we call folks to action to get out and participate in litter cleanups. And anyone that registers through Keep Pennsylvania Beautiful has access to free cleanup supplies such as gloves, trash bags, and often free or discounted disposal through the Pennsylvania DOT. And I saw another question pop up about data. We do collect data from the Schuylkill Scrub for the specific to the watershed there and post it on our schuylkillscrub.org. I'll drop the link in the chat if you're interested.
And I want to also, so that was in May. In April, on April 22nd is the annual cleanup at the John Heinz National Wildlife Refuge. It's a really impressive effort and they really need help in cleaning up. But if you have the extra energy to stay afterwards or can't make it in the morning because it's from 9 to 12 at low tide at the refuge, in the afternoon, we're going to be counting and sorting a sample of that trash, depending on how many volunteers we have. And we send that data to the Ocean Conservancy, who sends it to NOAA. There is an annual international coastal cleanup. It involves all water sites. And I think that has been so successful that it's just spreading to all times of year. So the data that you collect in one of these tools at all times of year will end up to NOAA and other international groups to try to understand where and what kind of problems there are around the world. So for example, Clean Swell and Crowd Water, the two apps that I put in the note for everyone, those can be used with your volunteers to collect the data, and that will go directly to the sponsoring organizations. But when we were collecting data, we wanted to see the data ourselves. And so we did paper counts so that we kept the data. So that's, I give that as an example of it depends what the question is that you want to ask.
Kaitie, what do you think about discussing the reflection question in the chat? Would that work?
Sure. And again, that was how can you take the information that you learned today and implement it?
So I suggest you keep, if you can click on the links to the papers and other resources, why don't you go ahead and collect them? You don't know if you're going to need them at another time, but if you click on them now, you'll have them for later.
Yes, and I will also highly recommend the other videos in the Friends of the Heinz collection on plastics on their website is a great resource to learn more about this problem in varying categories like advocacy and community efforts to change behaviors. Very well done.
Thank you. Sharon asked a really good question, which was, if a township doesn't have the ability to collect this data, like, can they get the findings anyway? And I would say that the best source of that is the paper that you have a link for there, Plastic Debris in Rivers by Van Emmerick and his colleague, because if you can just take that paper section by section, you'll find a lot of the relevant information that you're looking for.
Are there any parting questions for us before we sign off? We have a few minutes more.
I have a question. I was wondering, with the ban bills that have been passed around the region and the Derby and other places, was plastics data used for those types of bills? I know it was a lot of advocacy too, but can you speak to that point?
I would say I'm only aware of indirect. There was before the Pennsylvania legislature banned the bans, preempted the bans. The state finance committee and another special committee was collecting data on the costs of plastics. And I know that the Sierra Club, I participated with them, wrote a report delineating all the different costs that come from plastic pollution. So they had that. I know Westchester, some of the key, Westchester wasn't the first town to have the ban, but it was one of the early ones, and they've, you know, enacted it now. And they, Jim Wiley, who's a major, who's on several of their committees, and is part of the Sierra Club, and so I know that he had access to that. So that data on, you know, how much it's costing us to have plastic waste is available. But in terms of the amount in rivers, I'm not sure if that's what you were looking for, Faith. The amount in rivers.
No, I think that's good. And the transference of data, right? So we've seen different places that have been banning it. And I think some of us are struggling with how to do it within our own townships, right? We're bordering places. So it's important to kind of be able to use the information that's out there for that advocacy. So we appreciate that.
I can send the Sierra Club report to people if they'd like. Of course, it is kind of pre inflation, so all of the costs, of course, have gone up over time. But if you'd like to see, at least it gives you categories and general idea of how expensive the debris is, and that might be useful. I'm just going to put my email in here in case anyone wants to follow up with that. I know you can also go through Riverkeeper, but I'll put it in here.
That's great. And then we'll also be sharing information on the participants. It's about 2 o'clock, so I think we should probably wrap up. It's been a really great session. Thank you, ladies, and Faulds, Carol Armstrong, Kaitie Evers. Thank you for using the Mentimeter. That was kind of cool tool. And of course, Tim as well. We encourage you to visit the virtual exhibit hall page of the Watershed Congress website as well. And remember that all of these sessions that are recorded will be presented on the Delaware Riverkeeper Network's YouTube channel. Thank you for joining us and brainstorming with us all. We hope to see you in 2024 in Pottstown along the Schuylkill River banks in person or at the next year's virtual sessions. Have a terrific day, everybody. And thank you again, ladies and Tim, for your help and work.